As an example, let's consider what entropy and the notion of equilibrium means for the ideal gas. For the partition function of the ideal gas in the microcanonical ensemble, we derived the following equation. In order to obtain the entropy from the partition function, we know that we have to calculate just the log of the partition function, and then we obtain 1 divided by Kb times the entropy. What we now have to consider is that n is very large. So we will use Stirling's approximation, meaning that the log of n factorial is equal to n times log of n minus n, and the log of the gamma function is equal to the factorial of the argument. Using those approximations, we obtain a simplified equation where n is a prefactor and we have terms of the logarithms. Also note that the last term in the previous equation, which contains delta E divided by E, is neglected since it does not scale with n, so is small with respect to large N. Finally, we obtain a compact equation for the entropy of an ideal gas in the microcanonical ensemble. This equation is termed the Sackur-Tetrode equation and contains three terms. One in which we look for the mean volume per particle, a second one which contains the mean energy per particle, and a constant 5/2. If we now want to analyze the equilibrium between two systems, we have to calculate the partial derivatives of the entropy with respect to all the parameters. For the partial derivative of the entropy with energy, we get a very simple equation reading 3n Kb divided by 2E. If we do the partial derivative with respect to the volume, we obtain Kbn divided by V. And for the partial derivative with respect to the number, we obtain a somewhat more complicated equation. Now, for equilibrium between two systems, 1 and 2, we have to consider these derivatives. Let's look first for the energy term. Two systems in equilibrium, what this requires is that the ratio n1 divided by e1 should be equal to the n2 divided by e2. In physical terms, this means that the energy per particle in both systems should be the same. Likewise, if we now look on the mechanical equilibrium, which means that we look for the volume term, what we get is that the particle density in the two systems have to be equal. The third equation tells us about the chemical equilibrium. For chemical equilibrium, as derived from the partial derivative with respect to the number of particles, both the energy per particle and the particle density have to be the same. As a summary, we derived the Sackur-Tetrode equation, which describes the entropy of an ideal gas in the microcanonical ensemble. Further, we evaluated the equilibrium between two systems, and we found that for two systems to be in equilibrium is equivalent saying that the energy per particle and the particle density have to be the same.